So our next speaker this afternoon is Alan Marquez, who comes to us from Cal State LA, where he'll be a rising junior this year. Alan has worked over the summer with Alex, and he'll tell us about his project today, Inferring Stellar Labels from Optical High-Resolution Spectra with the Payne. Go ahead, Alan, whenever you're ready.
Yeah, thank you, Gwen, for the introduction. And I'd just like to give a thank you to all the staff and postdocs at Carnegie and my advisor, Alex, and our collaborator, Yunsen, and Gwen for all the support. And so I'd like to start with an introduction. So the overall theme in our project is we're interested in stellar archaeology. And what that relates to is that we're interested in the origins of stars, where these stars were born, and what created the elements in them. And I'd like to ask a question. I'd like to show a type of question that we, types of questions that we're interested in. So where are elements like gold, platinum, and uranium made? And to do this, we measure the abundances of certain types of certain types of elements, such as R process elements and alpha elements. And a type of question that we can answer is by measuring these two abundances, if they have a linear relationship, that adds more data to them being our process elements being created in core collapse supernova. And if we get a result that's more scattered, that adds more validity to the theory that our process elements come from neutron star mergers. And just to give a visual on what these two types of, what we believe is the creator of our process elements are these two images. And so I'd like to give a little more detail now. So how exactly do we do this? And we do this by collecting the spectra of stars using telescopes. And to be more specific, we use optical high-resolution spectra to measure the stellar parameters and the chemical abundances, which I'll call these two stellar labels for short, using spectroscopy. And to give a visual representation of the data once it's been processed after it's been collected through the telescope and everything, and this is the type of data that we work with. And the stellar labels that we're interested in are the effective temperature, the surface gravity, and then those two parameters let us know, they set the tone for the atmosphere of the star, and they let us know how far we are from the star. And then we're interested in the alpha over iron ratio. And in this case, I've listed a couple of examples of alpha elements, but for our case, we'll be using magnesium. And then we're also interested in the iron over hydrogen ratio. So what's the problem? Well, the current problem is that there's more data than can be analyzed. And what I mean by that is that these data sets with spectra are getting larger in size. So we're going from thousands to hundreds of thousands of stars per in these data sets. And to be more specific, the problem is that the current methods that we have are analyzing these by hand using programs. And the upshot of it is that we do yield more accurate results when we're measuring these properties for our stars, but at the cost of requiring a lot of time because we essentially need a person at every step of the analysis. So what we need is a newer method that is automated, can provide uniform analysis for these properties, and is time efficient. And our solution to that is the Payne. So what is the Payne? So the Payne is a neural network that's been trained on synthetic theoretical spectra. And what the Payne does is that it emulates full spectrum fitting, which is a way of saying it is able to fit all the absorption features present in any spectra at once. And this is a visual representation of that. You have the actual model and the synthetic spectra being fit, or the Payne is fitting the synthetic spectra. And the reason that this is important is because it allows us to measure the stellar labels that we're interested in that I mentioned earlier. But the problem with synthetic theoretical spectra is that they aren't perfect. And what I mean by that, it's very hard to capture all the physics that actually goes into the training set. And just a quick note that the Payne was originally trained to work with infrared spectra, and the work that I'll be showing is our adaptation to have it work with optical spectra. So the first step in our analysis is to see where specifically the Payne doesn't fit as well. And what I mean by this is that there's regions in wavelength for any given spectra that the Payne doesn't fit well, and we're going to have to apply masks. And I'm going to define what a mask is. So a mask is essentially a region in wavelength for any given star where we will not consider that when we're measuring our properties. And to give a visual representation of this, we have the data that's being fed into the model, and then we have the actual model trying to fit the spectra. And as you see here at this feature, there's an absorption feature here that the model isn't able to actually capture. It misses it by a certain amount. And then we have this other absorption feature here where the model is able to actually measure that feature. And what's really interesting about this feature here is that for this specific element, I can't pronounce it, but the point is that this is an R process element, and it's one of the types of elements that we're actually interested in. So the fact that we were able to find out that this isn't fitting well gives more evidence to why we need to fine tune our models. So the next step is how do we measure how well the model is fitting? And we're going to use a normalized residual for this between the data and the model. And from here on out, I'll be, when I mentioned the word threshold, I'll be referring to the normalized residual cutoff. So I'll actually define what a normalized residual is. So it's the difference between the model and the data, and we've accounted for noise when we're calculating this. So then this plot here actually shows, so these two plots are related. I've calculated the normalized residual across this specific chunk in wavelength, and it's mapped here. So as you see, when we pick a threshold of 1 sigma, anything that's 1 standard deviation or more away from it, we're just going to throw out and we won't consider it, and we'll apply a mask. And if it's if we choose a threshold of 2 sigma, again, if it's more than 2 standard deviations away between these 2 points between the model and the data, we apply a mask there, and it won't be considered when we're measuring our properties. And to sort of give a visual representation of what I mean by masking, in this left plot here, I have a threshold of 1 sigma. And as you see, for this absorption feature where it wasn't able to actually fit that well, we essentially throw this part out of the model. And to contrast that, when we have a threshold of 2 sigma, we are throwing away a lot less of the data. So the next step is to actually check the Payne for its accuracy for optical spectra. And what we did is we ran this on the Gaia benchmark stars. And what's really important about these Gaia benchmark stars is that they're stars that have been analyzed by a group of people, and the parameters or the properties of these stars have been agreed upon, and they're known. And here's a quick table showing a couple of the stars where we know the actual properties too. So the next step for us is to run the Payne at a range of thresholds and see what's the best threshold to run this at. So in this plot, what we have here is we have the star Arcturus, and on the x-axis I have the masking threshold, and on the y-axis I have the difference between the predicted value that the model gave out and the actual label that has been analyzed by hand. So it's like a frame of reference. And so we did this for the effective temperature of the star. And the thing that I want to note here is that when we have a more aggressive masking threshold, we're essentially masking more of the spectra. So we're throwing away more of the data. And when we have a higher masking threshold, we're masking a lot less, as you saw earlier. And the goal with this plot is to show that we're trying to get as close to 0 as we can. And this band that I've drawn here, this green area, is an ideal range for values that we consider good measurements. So as you see here, when we apply a more aggressive mask to the star, we are able to get closer to true value results, or results that are within plus or minus 50 Kelvin for this graph. And then this graph shows the same thing, but I ran it across all 22 stars in this data set. And again, it's the same trend. More aggressive masking yields more, we get closer to true value results. And I've also done the same thing for the surface gravity. And it's the same trend across these, our model has the same trend. More aggressive masking gets us closer to true value results. And then lastly, I'll show the two abundance ratios that we're interested in. And it's the same trend. So lastly, I want to show this graph that shows how much of the spectrum the Payne is actually fitting. So I have the masking threshold on the x-axis, and then on the y-axis, I have a fraction of the spectrum that's actually being not used or masked. So what's really alarming about this graph is that we're using optical high-resolution spectra. And the thing with that is that there's a lot of feature richness included in the data. And what this graph is showing is that we're throwing away a lot of that data and at the cost of giving us these accurate results. So what we would like to do in the future is improve these models and use more of the spectra for these stars. And an example of that would be to make our models better, and we can actually add our process elements into the Payne's training set. So in conclusion, what we have done is we tested the Payne using these Gaia benchmark stars, and the takeaway from it was that when we applied a more aggressive mask, we were able to get closer to true value results. And lastly, we created a new set of masks to add to this model for the model to actually consider certain regions in wavelength where if there's a trend across all these stars, we're just gonna throw these away. And then lastly, our goal is to use more of the high resolution spectrum and in future iterations of this. And my last slide would be on future work. So we're actually currently in the process of training the Payne on UU grid. And this is going to allow us to extend the range of properties that we're actually able to measure. And just last night, we actually ran this on 270 stars from the RPA survey, which measures our process elements. And this graph here, while there's not much info on it in terms of like labels and all that, what's really important to note here is that the trend that we're seeing with this graph when we measure the effective temperature and the surface gravity is that there is a red giant branch forming, and that is giving us very promising results. So with that, the takeaway is that while we're throwing away a lot of the data, the fact that we're able to measure so many of these stars in such a quick manner is very promising. And with that, I'd like to open it up for any questions.
Nice job, Alan. Questions for Alan on his talk?
I have a technical question now.
Yes.
If you do one star, you get a certain mask that fits that star. When you do 20 stars, do you do every star individually, or do you take the union of the masks for all 20 stars? Because it must the difference must affect the systematics of the whole project.
Yes, that's actually a really good question, and the answer to that is when we ran when we ran this analysis, we applied individual masks per star, so it wasn't like a uniform set of masks. But what we did after was across all 22 stars, we used like a threshold, or we used if 22 of these stars out of the 22 stars, if let's say like 10 of these stars had a region where like it always had to mask that region, then that's something that we added to the model. Because when we ran this, we weren't including those masks. We weren't creating a uniform set of masks. But moving forward, we do want to have a uniform set of masks across all these stars.
Great, thank you.
Yeah, no problem.
Other questions for Alan?
Well, maybe I have a comment of something.
Yes.
Andy again. So you're doing spectrum synthesis, and then you find you're sort of far out when you use all the lines, and then when you use the best lines, then you're getting a better result. And it sort of feels a bit like what doing it by hand would be anyway. You use the lines that you know are not blended, and the lines that have the really good GF values. And so there's that.
Yeah.
And I wonder, you could probably improve GF values of lines that you're using now and they give really bad results, and you could check across the extent of your training set to see, you know, okay, well, if I put in a different GF value, you know, does it make all the stars work properly or not?
Yeah. So Yeah. Oh, sorry.
Sorry. And then other ways people do this are, they have a training set of a bunch of spectra where they've been analyzed by hand, and then they find the sensitivity of each pixel, really, or of
Yeah.
each line to the result. And so then they're not plugging in anything. The labels are already there from the previous analyses, and it feels like that's a better way to do like this en masse machine stuff. It's different
Yeah.
than doing, but I just wanted to make that.
Yeah. So from my understanding, the difference between this and something like the Canon is that the Canon is more of a data-driven model, and one of the upshots of using the Payne is that it's restricted by ab initio models, and the upshot to using the Payne is, to my understanding, I could be wrong, but it's that we are able to work with higher resolution. We're able to work with a wider range of resolution for these spectra. But yeah, that's a really good comment.
Any other questions for Alan? All right, very nice job.